So in this video, we discuss dynamic tricks to avoid some of the overheads associated with branches, conditional branches in conjunction with pipelines. So let's just repeat the fundamental limitations that we have from the pipeline implementation we discussed so far. So the three hazard types are structural hazards, where we could have two instructions that compete for the same hardware resource. We have the data hazard, and that's, for example, the read after write kind of hazard that we spent the last couple of videos trying to avoid using compilation techniques. And then we have the control hazards. The problem here is that we don't know the outcome of the branch until late in the pipeline, and therefore we're going to produce some bubbles in the pipeline and lose efficiency. This is what I told you in the crash course, the very first lecture about computer architecture. So if you have a piece of code like this, where you have a branch, and if you don't know whether the branch is going to be taken or not, you cannot start to work on the next instruction. But if you employ a green little man that can make that guess for you, if it's a good green man that makes an accurate prediction, we can trust it. The outcomes, I mean, in speculation, can start to execute the instructions at the target of the branch, and assume that the little green man says we're going to take the Y branch here. We can actually start to execute instructions from this basic block before we know the outcome of the branch, as long as we are careful and make sure that they have no side effects on the architecture state until we know that the branch indeed was going to be taken. Going back to the pipeline now, this is the picture that explained what the problem with the finding out late in the pipeline stage whether the branch was taken or not. This brown instruction once more is the branch, and we have been able to able to have a correct execution here of this code by inserting 3 bubbles in the pipeline. So we haven't put any new instructions following this instruction until it has reached the final stage and we know whether or not this branch will be taken. Of course, what we would like to do would have been to, at this point in time where the program counter was pointing to the brown instruction, and we just fetched the brown instruction, to make a guess whether or not we would go back and start to execute the green instruction A again, or whether or not we should continue and execute some other instruction E higher up here in this program. This is where the little green man comes into the picture. So we're going to make a guess right here. And the little green man lives in the instruction fetch stage. The way we implement the little green man, we're going to discuss this down to some gory level of detail. But you can think about this as we have introduced yet another cache. Computer architects have very little imagination. Every time there is a problem, we introduce a new cache. And this cache, we can cache that could be indexed with the address of this very instruction. So we use the program counter to index into this cache. And we also have an address tag here that corresponds to part of this instruction. So what we hope to do here is that the contents of this entry in the cache would actually be associated with this very PC. So we have some address comparators and so on, the way we normally implement caches here, address tag and some kind of PC value. And then we can store some information about this branch. We can store guesses. Should we guess that it's taken or not? Where is it branching, and so on. So we call this structure a branch target buffer, a BTB. But before we really discuss how it's built up, we're going to discuss different algorithms that can be used by this green man to make its guesses. Because of course, what we like to do for this little mean green man to make a correct guess. For example, if it's common that we do jump back to the green instruction, we want this guess, the little green man, to say, my guess is that you jump back to instruction A, and then instead of just filling the pipeline with bubbles, we would like for the instruction A to be put into the pipeline, followed by instruction B and C, following this brown instruction, so that when the brown instruction comes to the branch, the stage where the outcome of the branch is known, we have already started to work on the green instruction, gray instruction, and pink instruction. So now we know the outcome of the branch, and we also remember what guess we made. So we can see if that prediction was wrong, then we can update the program counter with whatever the outcome of the branch should have been. So we put the correct address there. And we can also prevent side effects from all these speculative instructions because they shouldn't have been executed. So they shouldn't have any side effect. But since all of them have their side effect implemented in the last pipeline stage, all I have to do is to make sure that when they get to the last pipeline stage, they are not allowed to have any side effects. They cannot update the registers. They cannot write to memory. So that's quite easy to implement. Now let's look at what kind of algorithms the little green man uses. So a very simple algorithm would be actually not to use a cache. All we have here is that we just get some indexing bits from the address of the branch, the PC, and we use some of them to index into a vector, 1-bit vector, but we don't have any address tags and so on. So what this implies is that we think that this method is good enough for a guess. We guess that this very bit here is associated with exactly this program counter. It is may be associated with other program counters whose address bits that we use for indexing is identical to this one, but that's not super likely. If this is a popular PC, it's more likely that this bit is associated with it. So it's a good enough guess. And this bit, if bit is 1, we're going to predict that the branch is taken, and 0 if it's not taken. And we simply just keep the history of what we did last time with this very PC or whatever PC happened to update this bit. So if we predict that it's not taken and that prediction is wrong, we're also going to go back here and we're going to change this bit. So next time we're going to predict that it is taken. So this is a fairly good guess, actually. This very simple structure. Turns out that it doesn't have the stability that you would like to have in this kind of guess. So what people have done instead, and this is actually what is implemented, is to add a little bit of hysteresis. So we have 2 bits here, and we're a little more stubborn about our guesses. So 1-1 means it's a strong prediction that it's going to be taken. If it turns out, so as long as we keep predicting taken and that's correct, we stay here. If we predict that it's taken and turn out the outcome of the branch is that it's not taken, we are not going to change the outcome of our guess, but this is a less strong prediction. This is predict taken, but no, we're not super sure this time. So if we see once more right again that it's not taken the very next time, then we change our prediction to a strong prediction not taken. But if we, when we have the weak prediction here, see that it is taken, then we go back and we become stubborn again with a strong prediction of taken. This is actually implemented. This is having 2 bits is typically is stable enough to get good performance on many benchmarks. So we're going to look at an example here, a very, very simple example. We walk through an n by n matrix. And for each element in the matrix, we just write the constant 1 into that location. We assume that we have this kind of 2-bit prediction. We assume that it's going to be initialized to 0, 0. So it's a strong prediction not taken. That's the initialization. And we're going to execute that program. And my question is, roughly how many times will the branch prediction be wrong? So the answer here is it's n times it will be wrong. So what will happen here is that we start executing. Of course, there are 2 branches here in this program. The outermost branch, we're going to, after we've taken that branch twice, then we're going to figure out that this is a branch that always is taken, always for n times it's going to be taken until we fall out of the program. Last time it's not going to be taken. Same thing with the inner loop. It's going to take us 2 mispredictions to figure out that this loop is quite often taken. So we're going to have the strong prediction here that it's going to be taken. And we're going to make the right prediction n minus 3 times actually. And the last time we go in the loop, we are not going to, the branch is not going to be taken. So that means that our guess is going to be wrong the last time the loop. In this loop, we're going to fall out in the outermost loop, make the correct prediction. We're going to come to the innermost loop once more, and we're going to keep predicting that it's going to be taken because we're stubborn. We have a 2-bit value. So what's going to happen here in essence is we're going to make the wrong prediction once every time. Every time all of the n times that we will come to the, or actually n times we're going to fall out of the innermost loop. Those n times we're going to make the misprediction, so n is correct. Okay, I'm going to look at a slightly more complex piece of code here. It's a code that writes ones to the rightmost diagonal, or all the values to the right of the diagonal of its matrix. So it's looping over I, looping over j, and then we have an if statement here figuring out whether we're going to write a 1 or a 0. And we have the same kind of prediction here. We have 1, 2, and 3 conditional branches in this code, and we have some unconditional jump as well. So my guess, of course, I have the same question. How many times, roughly, will the branch prediction be wrong here? And the correct answer is 4n times. So what's going to happen here for each line? Let's look at one of the lines in the middle here. We're going to figure out that we are going to be in the else part of the if statement. So that we're going to predict else, predict else, predict else, predict else. Whoops! We are in the if part of that clause now. So that's going to be one wrong prediction. But we're stubborn, so we're going to make the wrong prediction twice. So twice we're going to make the wrong prediction until we figure out that now we're in the if part of the statement. We're going to predict if, predict if, predict if, until we come to the next line here. And then we're going to say, make the wrong prediction again, because now we are predicting if, and we're going to make 2 wrong predictions until we predict the else path, and so on. So it's going to make 2 wrong predictions per line. Two wrong predictions when we change from a 0 to 1, and 2 wrong predictions when we change from a 1 to 0. So that means we're going to make 4 wrong predictions per line. So that's why the answer is 4n.